Hello, my name is Benjamin Gochanour, and today I'm going to be presenting on a non-parametric, multiply robust, multiple imputation method for causal inference. I'm from the University of Oklahoma Health Sciences Center, and my co-authors are listed here. So first, a motivating example. Let's say you're interested in the question, what is the association between exposure to PFA class chemicals and kidney function? Let's say you have enhanced survey data, and your outcome and exposure variables are as listed here, and you're interested in the mean difference in the eGFR or the clinical index of kidney function between the two groups. So not adjusting for confounding may result in an inflated estimate of the treatment effect. So we'd like to consider potential confounders that may affect both the exposure and the outcome of interest, such as the ones listed here. Now we'll come back to this example in a bit. But first, a little bit of a problem setup in general. So we have a non-random assignment to two exposure/treatment groups, t equals 0 and t equals 1. We have a vector of covariates x that is fully observed, and we're interested in study variables y1 and y0 corresponding to t equals 1 and t equals 0 respectively, or an observational study with confounding, where we're seeking to estimate the average treatment effect mu1 minus mu0. So now the proposed method. We're going to follow this process for mu1 and for mu0 and then take the difference. So it involves first computing standardized scores and drawing a bootstrap sample where we fit the working models. Then we calculate distance between each missing subject and all responding subjects. Fourth, define the nearest H neighborhood. And fifth, randomly select a Y value from the nearest neighborhood and impute. And then finally, repeat steps 2 through 5 to obtain L multiply imputed data sets. So some advantages of our method. As a non-parametric method, it makes weak assumptions about the underlying data. Second, and perhaps most importantly, it is multiply robust to protect against model misspecification. This means that our method will produce minimal bias given only that at least one model is correctly specified. Third, Rubin's variance formula can be applied to our method, which is advantageous because of its simplicity. And four, the R code is made publicly available to aid researchers in implementing our method. So some brief background in the simulation study. We generated covariates X from the standard multivariate normal distribution and Z covariates, which were transformed versions of X to be used for the misspecified models. Y1 and Y0 were generated from two regression models. We wanted to compare our results with those of regression imputation, inverse propensity score weighting, and some other traditional methods. So first, before we get to results, a brief note about notation. We chose to use this 4-digit notation, where the first 2 digits denote the correct and incorrect regression models, respectively, while the second 2 denote the correct and incorrect propensity score models, respectively. So for example, for this estimator, we use the correct regression estimator, the incorrect regression equation, I should say, as well as the incorrect propensity score equation. So here we see our results, and we see for all cases where at least one model is correctly specified, our method exhibits minimal relative bias. The only time our method exhibits relatively high relative bias is when we have both models misspecified. So now a real data application, returning to the kidney function problem from earlier. When we have real data application, of course, we don't know which models are correct or incorrect, but we built two sets of covariates, one with stepwise selection from all degree 1 terms, and the second including all degree 1 and degree 2 terms, as well as the 2- and 3-way interaction terms, and then including these covariates or potential confounders here with a sample size of n equals 1027. So I'm not going to go into detail into these results, but we see that the unadjusted estimator here results in an inflated estimate of the treatment effect, while the multiply robust multiple imputation estimator produces similar results to those of the other adjusted estimators, and we see a non-significant treatment effect here. So for our code for this method, please see my GitHub page, and then the slides for this presentation will be posted to my personal website in a few weeks. And this paper will be submitted to Biometrics if you'd like to see additional technical details. Here are references. Thank you so much for your time.